Oh, I didn't see you there. I'm Ananya, of the team lead of Team 32, the Histohelix. Let me introduce you to my team.
Hi, I'm Cassie Romeo, and I'm the mechanical engineer.
Hi, I'm Grace Shaw, and I'm a systems and software engineer.
Hi, I'm Sam DiMatteo. I'm a biomedical engineer, and I'm your team's procurement lead.
Hi, and I'm Jack Monry. I'm a mechanical engineer.
In the intricate world of medical diagnostics, every second counts. At the heart of pathology labs across the globe, histopathology tissue blocks play a crucial role in diagnosing diseases, most notably cancer. These small blocks, which contain tissue samples from biopsies, are the key to unlocking vital information about a patient's health. But the process of sorting and orienting these blocks, it's painstaking and time-consuming. Each minute spent handling these blocks is a minute away from analysis and diagnosis. In an environment where time is of the essence, efficiency isn't just beneficial, it's crucial. Timely patient care depends on swift and accurate test results. Delays in processing can increase anxiety and uncertainty for patients awaiting diagnosis. This is why we bring the Histohelix, a histopath tissue block sorting module, which transforms the traditional process, automating the sorting and orientation of tissue blocks with precision and speed. Quicker turnaround times, enhanced accuracy, less stress for the staff, and most importantly, faster answers for patient. The Histohelix isn't just a leap forward in lab technology, it's a leap forward in patient care. And we're here to show you how we're setting new standards in histopathology to innovate, improve, and impact.
Here, you can see a 3D model of our system in SOLIDWORKS. Our system consists of 4 main subsystems: the input conveyor system, the flipper, the rotator conveyor system, and the output queue. Each of these subsystems are connected to each other by chutes that bring the tissue blocks through our module in a helix fashion. Now, let's take a look at the main objectives that help measure the overall success of our project. One of the biggest challenges that we have faced during our project is being able to receive tissue blocks at any orientation, since these tissue blocks are similar to snowflakes, with no two being the same. Nonetheless, our input conveyor system is designed to combat this issue while protecting the wax blocks from damage. In regards to the autonomous orientation process, once the blocks enter our system, they pass sensors that begin the sorting process, leading to a consistent output. As for the wax block integrity, much like the input conveyor system, the rest of the subsystems and their connecting chutes do not damage the wax blocks, ensuring the safety of tissue samples. Lastly, our system's output queue has been designed and approved by Roche to be able to interface with the parent module consistently. This is what our system looks like inside a refined housing that would integrate seamlessly with the parent module at Roche. All of the parts have been printed and assembled too many times to count, with many of the shown parts being on their 7th, 8th, or even a larger iteration.
The process of prototyping involves first making cardboard parts of the rotator and flipper. The flipper started off as 2 discs with 2 bumpers that stops tissue blocks that are upside down. Inspiration for the rotator comes from a toy claw machine with the intent of pushing the blocks 180 degrees. We decided our materials for 3D printing are PLA for our customized parts and TPU for our conveyor belts due to its stretchability and easy customization. We then started 3D printing our parts and continued to test and modify as needed. Some modifications include adding stipples and cleats to increase the friction between the belt and the blocks. Our preliminary input conveyor belt was a general conveyor belt with cleats at a low inclined angle with a general chute. We tested how our input system can handle a batch of tissue blocks and separate them one by one. We found that decreasing the overall width, adding taller cleats, and guided walls will help each block approach the end of the conveyor belt lengthwise. This next conveyor setups reflected those changes as well as included our preliminary chute design to assist in the transition of getting tissue blocks from the conveyor to our flipper. We approached a similar fashion with the flipper and rotator by 3D printing our preliminary design and testing it with the tissue blocks. Our first flipper design had a sharp bumper and didn't accommodate all wax block sizes. So our final version included lifting the ceiling wall as well as flushing the bumper to the ceiling. We also rounded off all edges to ensure safe user handling as well as minimize damage to the paraffin wax of the block. Our rotator went through less iterations compared to the other prototypes, but still involves necessary testing to see if rotating on the TPU conveyor belt was possible. Our final version was fully integrated with the working conveyor belt and has performed the necessary tasks we needed. Other parts in our system experience the same types of prototyping but involve more iterating to integrate electronic and hardware components best.
In this first demo, you will see the tissue block go through the system in such a way that it is flipped but not rotated. The block goes up the input conveyor and slides into and is caught by the flipper. The flipper flips the block into the next chute where it is picked up by the flat conveyor and stops in front of the camera. The system goes through our team's 7-step image analysis algorithm to find the diagonal of the block's cassette, which it uses to determine, in this case, that the block does not need to be rotated. This determination tells the system to send the block all the way through to the output chute. This demo shows what happens if the block does not flip but needs to rotate. The block goes up the input conveyor, slides straight through the flipper, and stops at the camera. The system then goes through our algorithm. The image is converted to grayscale and then a binary black and white image. It then goes through 2 morphological operations to sharpen the binary image and then outline the white sections. The algorithm then finds all the lines in the image above a certain length. Those lines are then filtered to only capture those in the bottom half of the image and those within a certain tight angle range. Finally, once the desired line is found, the algorithm uses the sine of the angle and the x-coordinate of the line's endpoint to determine if the block needs to be rotated, as it does in this case. The block is rotated and sent down the output chute.
We spent a little over $1,600 of the $4,000 given to us, which can be broken up into smaller categories shown here. Using this information, we estimate that Roche's cost of materials, labor, and overhead for each consumer-ready module will be somewhere in the range of $3,000 to $4,000. Now that you have an idea of what it cost our team to develop and create this prototype module, we can look at why this project is important. There are over 1.9 million new cases of cancer diagnosed each year in the United States alone. That means a whole lot more tissue samples need to be stored after their analysis. Autonomous systems like ours are becoming increasingly popular due to a staggering rate of staffing shortages in labs worldwide. The goal of these autonomous systems is to keep up with increasing demands, and our module could play a role in a system that Roche estimated could save labs up to a whole person's worth of labor each year. Here's a brief look at our deliverables for this project. We want to give Roche the ability to recreate our success while also providing them with our idea of the best path forward.
Embarking on this project and the development of the histohelix has provided key insights and direction for future advancements. Precision in prototyping matters, but so does size. In the future, it will be important to think about a more compact design without sacrificing functionality when refining our prototype. Making the module smaller will ensure it fits seamlessly into Roche's interfaces, maximizing its utility. Longevity is also crucial. We've learned the significance of using high-quality materials to prevent wear and tear. Investing in durability not only enhances the module's lifespan, but also ensures consistent performance over time. Moving forward, we recommend Roche continues to focus on these areas. First, further miniaturization of the module to integrate into their environments. Second, the exploration of advanced materials that extend durability and enhance performance. It would be also useful to develop it to be set for high volume production to be integrated into a widespread of labs.